The rock isn't lit from behind, and it isn't see-through. It, along with others, seems as though it is lighting up internally. For centuries, this internal glow has stumped people until a combination of geology and physics provided a clue to what is known as the Schiller effect today, and more about it can be found by taking the time to visit this website. Glowing from the inside, it's not magic stones. Labradorite is one of the most common stones that has this look. It isn't too romantic, while it may seem like it is, and the actual scientific term is Labradorescence. It isn't quite iridescence, as this occurs on the surface of an item. Labradorescence appears from the interior of the object, causing it to light up internally. If you turn the labradorite, it will begin to flash like there are lights being turned off and on inside of it. It is jointed by a more melodic adularescence, which has been named for adularia, aka moonstone. Unlike the irregular flashes of labradorite, moonstones have a more regular and gentler glow. Both of these stones, along with several others, create a quality that people refer to as shiller or shiller. This effect, which is officially called the Schiller effect, can be seen in various stones, including rarer samples, such as common quartz. It's rooted in both physics and geology. Helpful tips to make a moonstone. The moonstone is essentially feldspar. It's something that is as common as mud. In fact, this is a group of minerals that comprise approximately 60% of the Earth's crust, and they are probably much more common than mud. They are found in many forms, but each form includes aluminum, potassium, and sodium in various compositions. On one end of potential compositions you have feldspar, which is made up of a large amount of sodium, and on the other end is feldspar, which has a lot of potassium. After the feldspar material has been melted, then it is going to reform, at which point the sodium becomes solid. If there isn't anything but sodium-rich material around, this won't do anything unusual. If the melted mix is considered more heterogeneous, this is when things become more interesting. First, albite, the sodium-rich material, will solidify. Then, the orthoclase, the potassium-rich material, will solidify. The process absorbs all the potassium nearby, and what is left is a sodium-rich material, which is going to solidify and absorb almost all of the sodium. This creates a material that is potassium-rich, and the layers continue. Even though labradorite is a unique type of feldspar, and usually much darker, it will follow the same process. It's the layering that makes a stone shine. Now, you may wonder, how does the layering make the stone light up? Think of soap bubbles. When light comes in contact with a soap bubble, some of the light is going to reflect back. The remainder will travel through the soap film, but when the light transitions to the air in the bubble, some of the light is reflected back again. This results in several light waves being reflected out to the person looking at it. Since the light waves aren't in sync with each other, the troughs and peaks of the waves begin to overlap, which create different frequencies of light, which is seen as different colors. When the angle of the light changes and the soap bubble's thickness changes, the light frequencies change, and you see swirling patterns of color. This same effect occurs with feldspar. The light will reflect off the layers slightly differently, which results in the different colors. Also, the waves of light are broken up frequently, so they are only seen in flashes, thus the effect described above.